All right, off we go. Um, all right, another fun graph algorithm lecture. At least for me, graph algorithms are always fun. So today's about packing and covering paths. It's really a question about kind of connectivity and how well connected things are in a graph. So the high level kind of question we're interested in is you're given like a directed graph and maybe two vertices, S and T, and you kind of want to know how well connected S and T are in the graph. We'll quantify that. Um, Source and sink. S will always be calling a source and T will be calling a sink. It's not necessarily a source and sink in the sense of DAGs from before. It's just that, yeah, we'll often have an S and T vertex that we call a source and sink. It'll make a little more sense when the problem comes up. But yeah, so at a high level, we're interested in these questions of connectivity. What are some contexts? So, I think actually an early reason this problem was actually studied had to do with like military kind of operations research and physical infrastructure. So they were looking at problems of like, okay, so this is like I guess a train network of Eastern Europe or Western Russia or something. And at some level, if you wanted to have some air raids and disrupt a few railroad lines, right? You can drop some bombs or something and break up a few railroads. How can you be like as disruptive as possible and break up the network and stuff like that, the railroad network? So I guess yeah, some American operations research is studying these Russian railroads in the Cold War or something. And so that's also, analyzing networks and trying to find weaknesses in networks, trying to break up a few rails that maybe would be most disruptive. Okay, so that's an example. Um, I think CPUs, is another place where you want to not just make sure things are connected, make sure they have like robust connections, extra connections, stuff like that, especially since actually individual parts of CPUs fail all the time. You want to have like a robust network. When studying, like social networks and stuff like that, you know, um, how well connected something is might kind of tell you like, how, how many different ways there is to get from one friend to another via other friends or something like that. But maybe some kind of strength of connection somehow reflects stronger relationship or something between two things. Anyway, another one, another kind of network analysis kind of situation is something like the World Wide Web or something, right? And so when they're doing things like PageRank, they want to figure out which websites have a lot of other websites kind of pointed to him in a lot of ways. So a really important website will have a lot of kind of incoming connections and will be kind of well connected, at least in an incoming sense, to other websites and stuff like that. But these are just kind of high level examples of where you want to do a network analysis beyond just reachability and beyond just shortest path. So, okay. What are some different ways to ask the question of connectivity? What are some different ones? So here's maybe one that we've already done, just the question of, is there a path from S to T, right? That's maybe a simple question of connectivity. Is there any connection at all between S and T? Of course, we can now use breadth first search or depth first search and stuff like that. That'll answer that question pretty easily. A second question might be like, how many different paths are there from S to T? Okay, so there could be like exponentially many or not that many or something like that. I'm actually not sure what the best way is to solve this. I don't know if it's solvable. One that is solvable is, suppose I fix a number of hops, like 10, and say how many ways is there to get from S to T while using at most 10 edges, right? So if you're studying like a social analysis, maybe K is like 2. So it's like how many kind of friend-to-friend relationships are there between these two people? That's another way to try to measure connectivity. Another way might be what's the length of the shortest S to T path? Maybe in some context you would think if they're very close to each other, they're more strongly connected in some way. We also know how to solve this problem, of course. That's breadth first search. Here's a problem that shows up in an exercise. How many shortest S to T paths? So maybe, okay, you already know that this person is 3 hops away from that person, but within that, having lots of different paths of length 3 maybe is a stronger indicator than having few paths of length 3. All right, here's one that actually is used when analyzing the internet and doing things like PageRank. If I started at S and I randomly walked around the graph, so like step 1, I have 2 possible edges, so I'll just flip a coin. And if it's like heads, I'll take the top edge, tails, I'll take the bottom edge. Say it's heads, so I go this way or something, right? And I flip another coin, it's tails, I go this way. But you just keep flipping coins, you randomly walk around the graph. It's called a random walk. What are the odds that you'll get to T, or what's the expected number of steps until you land at T? Okay, so this is actually used in PageRank. But the idea being that, if there's like a lot of ways to get from S to T, then hopefully a random walk has a better chance of going from S to T and stuff like that. And in some cases, you can actually try to calculate these quantities, or you can run some simulations. All right, that's another way to ask this question. Okay, here's another version of the connectivity question. What is the maximum number, not of paths from S to T, but edge disjoint paths from S to T? Okay, so you're trying to find a lot of paths from S to T, but they can't use the same edge as each other. That's the rule. Okay, so for this problem, what would be the maximum number of edge disjoint paths from S to T? Two? Okay, I heard two. Okay, so I'll start here and you just tell me, like, describe the path to me. So the first path, should I go up or down? Down? Okay. Up, like the upper one or bottom one? Top one, okay. And again, top or bottom? Bottom. Now I guess you have 4 choices. 1, 2, 3, or 4. I can go right or kind of up to the right or straight up or to the left. Right, okay, we'll keep going right. Okay, I can go down or I can go up right or I can even go down left. Up right, okay. And then from here, I guess I only have one. Oh, I can go up or I can go down. Down right, and then I guess go right. Okay, so that's one path. All right, now let's start a second path in green. I guess here it has to be edge disjoint, so now I only have one choice left. I can only go upwards. Okay, now should I take the upper path or upper edge or lower edge? Upper, okay, let's go upper. Here I can go straight down or I can go to the right. Okay, so someone say right. All right, now I can either go down to the right or I can go up. All right, we'll go down right. And then now I can either kind of go down left or down right. So if I forget to draw arrows, I guess that just means you can go either direction. Down right, okay. So they are allowed to share vertices in this model. It's just the edges that have to be disjoint, so this is totally okay. All right, and then from here, up to the right, okay, and then up to the right, and then down. Okay, so this is relatively interesting since they kind of cross each other. 2 edge disjoint paths from S to T. Could anyone do better? How do you know you can't do better? Yeah, so T only has two edges coming in, and actually on the other side, S also only has two edges going out. So those are two actually certificates that prove that we have an optimal solution. In general, it might not be so obvious that you have an optimal solution, but here we actually know we got the right one. Okay. Well, oh, why did I put the word max there? Well, okay, so the high level, okay, so if we're zooming out, the high level question is what are some different ways to quantify the strength of connection between S and T? And so one natural thing is, I mean, here the question is, what's the most edge disjoint pass you can put from S to T? So if the max is bigger, that maybe reflects a stronger connection. Whereas like if it's just like having one disjoint path, well, yeah, like maybe like having seven disjoint paths is a stronger connection than three or something. So max is just to emphasize bigger is more connected. Yeah. Yeah. So if I just wrote the number of edge disjoint S to T paths, is it the same? Well, okay, this is just an English question. Uh, I, I'm actually not sure. Uh, we can have a vote. Uh, if I hadn't put the word max here, would it have the same meaning for you? Most of you, or would it have a different meaning? I like having the word max there personally. I feel like max makes sense. I'm not even sure how to interpret without max there. Well, okay, so I mean, I think edge disjoint. This is such a silly conversation. Edge disjoint already indicates some kind of like constraint where you can't take everything, right? So it has the feeling of there ought to be a max there. Um, anyway, redundancy is okay in any case because it just makes it extra clear. Okay. Okay, Max, I bet you're one of these programmers who use very small variable names and it's impossible to read your code. It's just like, oh, X is equal to Y plus Z or something. It's like, all right. Okay. Descriptive variable names, redundant descriptions. Yeah. Okay. We're not even using real ink, so it's okay to write extra. Okay. All right. So that was a max number of edge disjoint paths, also known as number of edge disjoint paths, I guess. Okay. Here is another question, a way to try to measure connections, maybe more related to that railroad example. What's the minimum number of edges I would need to delete to make sure that I can't go from S to T anymore? And I know you're thinking, do I need to put min there? But we're not having that discussion. Okay, so what's the minimum number of edges I would need to delete to disconnect S from T? Two, okay, what are an example of two? Okay, the first two. So if I delete these two, then I can't get. Okay, also on the sync side, if I deleted those two edges going into sync, it would be two. Can anyone do one? Can anyone explain why we can't do one? Oh, we have two edge disjoint paths. So you're gonna have to take at least one edge from each one. Okay. So in fact, these, in this particular example at least, mutually certify each other to be optimal. 7 is actually always less than or equal to 8. Okay. All right. So anyway, those are a bunch of different kinds of questions, and I could think of more. I just made some list one day, and this is what came to mind. All right, but they're all examples of kind of network analysis of some kind. Okay, so we're going to be interested in the last two questions today, the maximum number of edge disjoint paths and the minimum number of edges you need to delete to disconnect the two. So this question, the maximum number of edge disjoint paths. What is the maximum number of paths? So I think of this, and I'm going to formulate this as sort of a packing problem. Okay, so packing problems in general refer to problems where you're trying to take a lot of something, but you're facing some kind of like size constraint or something where you can't take everything. Okay, so in this problem, I'm kind of thinking of taking paths from S to T, right? And I want to take as many paths as possible, but they share some resources, right? Because each path uses a set of edges. So once I take a path, I've used up all those edges. So those are sort of the packing constraints. I'm trying to pack the paths into the graphs, but I'm constrained where I'm only allowed to use each edge once. Okay? Because this is not the only packing problem we'll see. Okay, so so in that version, question 7 is trying to get the maximum cardinality path packing. Trying to get a packing of paths in the sense that it's feasible. It only uses each edge once, otherwise of maximum total size. Okay. This is another example of a packing problem. Okay, so the path packs into an edge E and P. I would argue that maybe it's our second packing problem. Can someone think of a packing problem we did recently? So the maximum forced problem we did last time, you could think of it as trying to take a lot of edges, but from every cycle, you have to leave out at least one edge. Right? So every cycle is 10 edges. You can only take 9 of them because if you complete the cycle, then it's not a forest anymore. So in that sense, you could think of the forest as a packing problem, trying to take as many edges as possible, but you're constrained so that you can't take all the edges from any single cycle. Like a fancy way to say acyclic, but it helps unify. This packing covering is coming next framework helps understand a lot of problems. Okay. The other problem, again, that we're focusing on is trying to figure out the minimum number of edges you need to delete to disconnect S from T. Okay, so first, there's some terminology. This is sometimes called an ST cut. Okay, so in general, a cut is like really a set of edges, but often like you have a set of vertices over here, and in the cut of edges leaving it, so let's call this U. And the edges leaving U is sort of the outcut, so to speak, and it will sometimes be denoted as delta plus U. Okay. So all the edges leaving U will form a cut in the sense that if I remove it, then you can't leave U anymore. It'll cut off U from the rest of the graph. So an ST cut refers to a set of edges. If I remove it from the graph, I can't get from S to T anymore. Okay. All right, so in this terminology, the more conventional way to ask for question 8, is to ask for the minimum cardinality ST cut. Okay. This is min ST cut problem. And I can think of this as a covering problem. Okay, so last one was a packing problem. This is a covering problem. So in a covering problem, you typically want to take as little of something as possible, but there's certain like minimum requirements. You have to cover this requirement. You have to cover that requirement. So you can't just take 0 like you'd want to. Okay, so we can think of this as a covering problem where an edge will cover any path that contains the edge. Okay. And now the goal is to take a set of edges that covers every path from S to T, which is to say I take at least one edge from every path from S to T. And if you do take at least one edge on every path from S to T, then you can't get from S to T anymore. Okay. So in that sense, we can call it a covering problem. Okay, so okay, that was supposed to be a slide on itself. All right, so we have an example of what's sometimes called duality. Okay, packing and covering duality. So in the path packing problem, I'm packing paths into edges. In the ST cut problem, I'm taking edges to cover all of the ST paths. Right? So there's actually quite a lot of symmetry between these problems. They feel like two sides of the same coin. A packs into B, and B covers A. Give me the most A that packs into B. Give me the least B that covers A. Okay. So kind of standard packing covering setup. So our first lemma, and this actually applies whenever you run into a packing and covering kind of situation, as we'll see. Our first lemma is going to say that the maximum number of disjoint S to T paths is always at most the size of any S to T cut. All right, so maximum number of disjoint S to T paths is at most the number of edges in any S to T cut. All right, so how are we going to prove this? Okay, so let's let P, capital P, script P, denote like a family of edge disjoint S to T paths. And C be a set of edges that forms an S to T cut. Okay, so P, everything's going to be edge disjoint. C, everything is going to separate S from T. So on the right, I sort of drew kind of like a high-level diagram of what that might look like, right? So the red represents some paths going from S to T, and the C is just some block of edges that's sort of separating the two. Okay, so I want to show, right? I want to show that the number of paths in my packing is at most the number of edges in the cut. Okay. How might we do this? Any ideas? I want to argue yeah. Oh, yeah, okay. 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 Close. Close. Off to a reasonable start. Okay, so one thing is, okay, I can take my family of paths, there's say 10 paths in here, right? So let me just first write something that's not very interesting. I can sum over all the paths and just write 1, right? 1 point for each path. That'll give me the total size. Okay. So so what do I know about the cut compared to, let's say, a single path, P, I guess. What do I know about the cut in the path? It's not unique to the path. Sorry? The cut will have at least one edge from the path. Okay, so, if I look at the intersection of the path and the cut for a particular path, that's at least 1. So I've replaced the 1 with P intersection C, because there's always at least one edge. Okay? And okay, so now for each path, I've kind of chosen one edge from the cut that disrupts it, or at least one edge, right? And, okay. And what do I know about these edges? Can they be the same? Okay, how come they have to be different? Because the paths are edge disjoint, right? So the paths are all going from S to T. They're using different edges from the cut because the path themselves are using different edges. So that means if I took the union over all the paths of that overlap. I'm not double counting anything, right? They're all disjoint edges. Okay? And then finally, the union, they're all subsets of the cut, so the whole union will be at most the cut. Okay? So I don't know, maybe that's too mathematical. Really, the argument is just you have all these paths, each path has at least one edge from the cut, and they have to be different edges. So the number of paths is at most the number of edges in the cut. Okay. All right. But we talked about paths and edges in a cut, but really we did nothing more than leverage this kind of packing covering duality. If I had given you any kind of packing and covering setup, you could have done the exact same proof. Okay, so this is sometimes called the easy direction of this duality inequality. Okay. All right. So we've established that. Okay. So we have, one sort of structural lemma on our side, which is that the maximum number of disjoint paths is always at most the size of any SD cut. That we know, and that was not too hard to show. Okay, let's move on to, we'll eventually strengthen that relationship, but we're going to start talking about things algorithmically as well. Okay, so the question is, how do you compute the maximum number of edge disjoint paths? Okay, and now I want to come up with an algorithm. Does anyone want to throw out some fun, intuitive algorithms? Any ideas come to mind? An algorithm for computing the maximum number of edge disjoint SCT paths. Or put alternatively, how did you solve this example earlier? Yeah. Yeah, okay, so we can, yeah, if I remember correctly, I think this was one of the paths. Went this way, down, right? So we found one path like that. And then if you want to make sure you don't use those edges again, we can delete them. Let me painstakingly delete these. Uh, so I can delete these edges, and then good. Now they're taken out, so I can't use them again. And then we could run breadth first search, depth first search one more time, and that'll give us our second path, which was, that's not it, something like this. And since I deleted those edges, I won't reuse them, right? Okay, so this is a very natural idea. This is sort of like a greedy idea, let's just keep just removing paths and stuff like that. And at the very least, I will end up with a maximal solution, right? I'll end up with a set of paths and I can't stuff any more paths in there. So it's kind of like locally maximal. The question, of course, is it maximum? Okay. Who thinks this is going to be a correct algorithm? And then who thinks it's going to have some issues? Okay. Now, for those who think that it might have some issues, then, can you think of a counter example, a simple example, where this greedy algorithm, which I think is the most natural idea, a simple example where it might not work? Yeah. Okay, so I'm just going to push you for fun because I'm a teacher to be more precise. So, okay. So I kind of loosely drew two disjoint paths from S to T, but now let's make this into an example and flesh out this idea. So I guess you're trying to think of a third path that would block both of them, maybe? Okay, let me make this a bit more. So I think a relatively minimal example where you have two edge disjoint paths might first look like this. Okay, so this is pretty close. Now, how can I make a small adjustment to this to give me a bad graph? All right, so I think if we add this edge here, it'll satisfy what you're describing. Okay, so we have, if you went all the way on top and all the way on the bottom, you get two different ones. But if you weren't careful and you took the middle edge, then that's no good, right? So that's what I had here. Okay, so the good solution would look like this. A bad solution would look like that, right? So it does seem like you need to be somewhat careful about which paths you take. You can't just take any path you want. If you choose the wrong one, you won't get the right solution. I can take this kind of counterexample and exaggerate it. So take something like this. How many edge disjoint paths does this have? Four, right? So if I went all the way across the top and, right, so we have four. But what would a really bad choice of path look like? Okay, I see some fingers moving around, right? This would block all four and you'd only end up with one. Of course, nothing special about four. I can make a million of these layers. So, okay, so a simple greedy algorithm doesn't work. So this is already different than last lecture. It turns out last lecture, greedy algorithms do work, but that's because spanning trees are so well behaved. This apparently is not quite so well behaved. Okay. All right. Okay. So that's the issue. This very natural algorithm, removing all the edges. You know, if I applied it to the graph with the wrong thing, it obviously leaves a disconnected graph right away, and you're screwed. Okay. So now the question is, how can we rectify? I mean, it still makes sense to try to choose paths from the graph, but it's a little hard to figure out what's the right way to choose a good path, right? Okay. So I think the next idea is a little bit of a clever twist. So, okay, right, okay. Okay, so what's going on? Okay, so I think the initial idea of let me find a path and rip out all the edges is very natural because it guarantees you'll end up with a disjoint set of paths. It's certainly sufficient to get edge disjoint paths. But the question is this necessary? Okay, so here's a slightly different perspective. So, okay, look at this sort of like, it's really more of a metaphor. Look at this sort of like a pseudo algebra of paths. Okay, so here's sort of like two paths, one that goes up, down, from your point of view goes like this, and the other one goes like that. Okay, and I add them together, and I get like the two outer paths, and I have both directions in the middle. And I can decompose this into an upper path, a lower path, and then sort of some leftover middle edge to sort of cancel each other out. Okay. But what's the point? So this here is sort of like the bad path in our original graph, right? And here, these two edges, and I'll do a different color. These two edges are left over, right? And I've sort of introduced a new fake edge in the middle. Okay. And what's nice is that when you add them up, it does sort of like contain two paths in the original graph, two edge disjoint paths in the original graph. All right, I'm speaking a little bit ambiguously, but okay. You know, in some sense, I could think of these opposite edges as sort of canceling out. Okay. And maybe after I choose one path in the original graph, I should be allowed to use the opposite directions of the paths I already took, because I might be able to cancel them out in some sense. So after taking that bad edge, you know, if I add in the reverse edges, okay, now in this remaining graph, there is a path, again, to go from S to T. It's not really a path in the original graph because I've introduced this fake edge. But at least in this particular example, my two kind of three edge paths I've taken can sort of be added up and then re-separated into two edge disjoint paths plus that middle edge which sort of cancels out the original direction and the fake direction. Okay, so this is just to build some ideas. Here's a little bit more of a formal lemma. Okay, so suppose I have two edge disjoint paths, P and Q. So I guess P is the one in red and Q is the one in purple. Okay, and they're edge disjoint, although they could be using opposite directions. So that counts as edge disjoint, even though one is going down and one is going up in the middle. Okay. The claim is that if I have something like this, then it contains two edge disjoint paths, P prime and Q prime, that don't have any of these opposite pairs of edges. Okay. So in this kind of caricature of a picture up there, you know, one path is like, oh, here's one, and here's the other, right? So that gives you two edge disjoint paths contained in the union of the two original paths. But these two edge disjoint paths don't even have any opposite direction edges. I can kind of cancel them all out. Okay. So this is not so hard to prove. We can do it by induction on the number of these opposite pairs that the two paths have in common. So in the base case, P and Q don't have any opposite pairs, and we're just done. In a general case, there might be a bunch, right? So maybe here's the red path, and here's the Q path. Every time they overlap is supposed to kind of suggest they're kind of crossing, and I'll just identify one of them. Like here's one pair where they're crossing, and then I'll just remove it and kind of replace the ends, right, so to speak. So in other words, what I would do is erase this. Oh, that's not right. Erase the edge that they were sharing in the middle in opposite directions. And then I would sort of take, you know, so purple is going around, and now I've cut off purple. I'm going to reach the green vertex, and I'll just use the red part to finish. And likewise with red is kind of going through, it runs into that green vertex, and I'll use the purple to finish, right? So that will look more like, if I draw over it, that'll become purple, that'll become red. Okay. Now I have, again, two edge disjoint paths, and the number of reversed pairs of edges has gone down by one. So by induction, I can just take care of the rest. Okay. Or you don't even need induction, whatever. You just go one at a time until you get rid of all of them. In fact, it's not hard to do this in linear time by just kind of working backwards, but that's another. Okay. Okay, so the point though is actually these reverse edges are actually kind of nice. They actually can cancel each other out and stuff like that. So that when I'm looking at okay. Okay, so that suggests now the following algorithm, which is just a slight adjustment upon the natural greedy algorithm that was first suggested. So previously our algorithm was, hey, take a path, remove it from the graph. Take a path, remove it from the graph. We know that might have some issues. The only thing we're going to do different now is that we're going to take a path, okay? And instead of just removing all the edges from the graph, and I have an example coming up, we're going to add all of the reverse direction to the graph. So for every edge I take from S to T, I'm going to add back the opposite direction, going back from T to S. Okay? Knowing that if a future path takes it, one of these edges, that'll imply one of these opposite pairs that I can uncross later. Okay? So that means like after your first iteration, your graph starts to look more and more different because you're adding all these auxiliary edges that weren't part of the original input, the reverse edges of edges you've already taken. Okay? And so you keep looking, you add the reverse of all those edges to the graph, and then in the next iteration, you might find a new path, and it might be using some of these auxiliary edges, some of these reverse edges. And we know from the previous lemma, we can kind of uncross those edges and get two edge disjoint paths just using the original edges of the graph. Okay, so for our simple example that we keep coming back to, because it's within my drawing capabilities, right? All right, so what happens in a bad case? I choose that middle edge, right? And I use up everything, okay? But now instead of removing everything from the graph, I'm going to add all the reverse edges. So if you look carefully, I've redrawn the arrows to go in the opposite direction. There's some arrows in teal. It's now going in the opposite direction, okay? So now when I look for a path in the next iteration, I can use those new arcs. So next iteration, you find this path, okay, which is using that new arc in the middle, which is a reverse of an arc we've already taken, okay. And by the previous lemma, I can uncross those two paths, okay. And what that does is actually adds back in the original edge to the graph. Okay. All right, so then you end up with something like this, where I have an upper path, I have a lower path, and I've added all the reverse edges back in. And now there's no S to T paths in the final residual graph. So somehow you keep taking paths and adding the reverse edges, take a path, add the reverse edges, and eventually you can't get from S to T anymore, and that's when you terminate. Okay, so adding those reverse edges might let you squeeze out a few more paths than if you had just ripped out the edges from the graph. Okay, so at the very least, it seems more aggressive. We don't know yet that it works or not, but it's certainly more aggressive than just removing the paths completely from the graph. Okay. All right, so for what it's worth, these intermediate graphs that include these reverse edges is sometimes called a residual graph, because based on the paths you've already taken, that's sort of like the leftovers, including the reverse. Anyway, it's just a word. So that's called the residual graph. All right. All right, so now what we got to do, and this is I think, the deeper part of the class, is to try to prove this algorithm works. It's clearly non-trivial, right? It's not at all obvious that it works. It's doing something very clever by adding the reverse edges back to the graph, which seems safe. It does produce a feasible solution, but it seems quite hard to, I think, prove that this thing actually works. Yeah. Yeah, so if there was, okay, so let's say I took this example and I don't know, I just added like one more edge like this, maybe a vertex in the middle, and one more edge like this, another vertex in the middle, and then I, uh, I find another path, right? Then, yeah, I would immediately add the reverse and then it would get flipped back up again. Yeah, and I just keep flipping, keep flipping. It's all okay. Yeah. Okay. And many times, I'll make another word. Many times you're not even interested in actually getting the pass. You just want to know the quantity, right? Then you don't have to literally uncross it. You just add the reversed edge back into the graph because you know that's what would happen. Okay. Another comment is that, um, well, yeah, okay, I'll leave that for the next time. Okay, so, all right, so, okay, all right. Okay, so anyway, so this is the algorithm. You're adding the reverse edges. I guess before I start the next part, we're going to try to prove it works. Does anyone have some high-level ideas or suggestions as to how to begin to even prove this thing might work? I'm just kind of curious. I don't know what people would come up with. I feel like this is highly non-trivial. At least if you're stumped now, you might be more impressed when we eventually prove it. Or more tired of me, I don't know. Okay. All right, so let's try to prove this thing works. This adding reverse edge trick works. Okay. All right, so here's the setup. Okay, so when the algorithm terminates, right, you've made a bunch of changes to the residual graph because you've taken a bunch of paths and you've added a bunch of reverse edges and stuff like that. And all I know is that at the end of the algorithm, by the time I'm done, I can no longer get from S to T. Okay? So you might have like some set of vertices that S can reach drawn in green, right? And then at that point, there's no edges leaving S anymore. All the edges must be coming back to S, right? Because if some edge was leaving S, then S can also reach that vertex and go across that edge, right? So at the boundary of S, edges are only coming in. Or at the boundary of the green, edges are only going into green. And then maybe orange is all the rest of the graph. So conceptually, it looks something like this, this kind of sketchy picture. Okay, so we're going to introduce some notation and label these parts. Okay, so I'm going to let big S, which since big S looks like little s, I started putting a line under it. So capital S denotes the set of vertices that is reachable from the source in the residual graph at the end. Okay, so we're kind of looking in hindsight. And big T, or T with a line under it, is everything else. Okay, and that splits the graph into two parts. Okay, and so I have the source, and I have some set of vertices kind of like around the source, at least conceptually, and then I have everything else. Okay, and what I'm going to do is I'm going to focus on the edges leaving S from the beginning of the algorithm. So at the end, there's no edges left that's leaving at capital S. But originally there was, right? Once upon a time at the beginning, maybe there was. So, all right, it might look something like this, right? So let's say the green is the set of vertices. So this is a picture of the input graph, maybe, like what is started at the beginning. It's not a perfect picture, but anyway, just imagine. Okay, so this is like the input graph, and maybe the green represents the vertices that the source can reach at the end, in the final residual graph. And then orange represents everything else. Okay. And what I've done, I've highlighted in yellow from the input graph, the set of edges leaving the green. Right? So that's a cut, separating S from T. That at the end of the algorithm is completely depleted in a sense. right? There might have been some edges there at the beginning. At the end, there's none of those edges left because S can no longer reach T. Okay, so we're focusing on this cut, this particular cut of edges leaving the green, leaving capital S, where again, capital S is a set of vertices that the source can reach at the end. Okay, so let's focus on this cut. Okay, so over the course of the algorithm, what's happening to this cut, right? So let's say that I find, let me choose a good color. What does the algorithm do? The algorithm looks for, let me choose an interesting one. The algorithm is going to look for a path, of some arbitrary kind from S to T, right? This is quite arbitrary. It's not at all a very short one, okay? But it's a path from S to T, okay? It actually uses more than one edge from that cut C. It uses two, okay? So I can't say that like, oh, this path always only uses one edge from the cut. But, okay, so, right, so in blue, I've highlighted the edges that are sort of coming into green. Okay, so the blue edges are going backwards. The yellow edges go forwards. The blue edges are going backwards in terms of this green-orange split. And so although this purple path has two yellow edges, it does have one blue edge, one edge coming back from orange to green. Okay. Now I know that the path starts in green, it ends in orange. So maybe it just uses one yellow edge and just goes there, right? Or maybe it goes back and forth, back and forth, back and forth, back and forth. But I do know that at the end of the day, it's going to use one more edge in this direction than that direction, right? Because it has to end up in orange. So maybe it does go back and forth. But I know for sure there's exactly one more edge in the forwards direction than in the backwards direction. Okay? So every S to T path and whatever path the algorithm picks is going to have one more edge going from the green, capital S, to the orange, capital T, then from the orange, capital T, to the green, capital S. Okay? Just because you're trying to go from one side of the bridge to the other, one side of a river to another, so you're going to have to ultimately go in the forwards direction one more time and then the backwards. Okay. All right, so what does that mean to the residual graph, right? So after I choose this path, I'm going to add all the reverse edges, right? So that means I'm going to lose some of those yellow edges because they're going to now get flipped. But then some of the blue edges flip over and become yellow, right? But what's the net difference? Yeah, so originally I have one more going forwards than backwards, and then you get reversed. So that means the total number going forwards goes down by one. Okay, so as I kind of observe this cut over the course of the algorithm, the number of edges leaving green and going to orange will go down by one in each iteration. Exactly one. Okay, so each iteration, the size of the edges in the cut, the S to T cut, has gone down by one. Even if it used it like 10 times, but that means it used 9 in reverse, so then the net change is 1. Okay. All right. Now at the end of the algorithm, how many edges are left in C? Yeah, it decreases by number of paths. And remember, how did we choose C? We chose C because this was like the frontier of the vertices S can reach in the residual graph. So what does that mean about C? So each time it's going down by 1, but what happens at the end? 0. right? This is a cut that gets driven all the way down to 0 by the end of the algorithm. That's how we chose it. Okay. So like this picture doesn't have any yellow edges left. There are only blue edges going backwards. Okay, so, all right, so at the end, there's no edges left in the cut. Okay, so every iteration, I pick a path from S to T, and the number of edges in that cut goes down by 1. And based on how I chose that cut initially, at the end, that cut has 0 edges left. So now, how do I relate the number of edges in the cut originally to the number of paths I picked? If I pack 100 paths, how many edges were in C? At least 100? Okay, can anyone be more precise than that? Exactly 100. Each iteration, the tally goes down by exactly 1. Every path I pack, number of edges go down by 1. Number of edges go down by 1. At the end, I'm at 0, and I've packed 100 paths. So, what we've shown then is the number of paths we packed is exactly equal to the number of edges in this particular cut C, originally in the graph. Okay. All right, so that's the argument we've shown, right? Is that at the end of the day, the number of paths that the algorithm packs, yeah. Because then it would still be at the end, then so if there was an edge that we hadn't used, right, then it should still be hanging around at the end of the algorithm. But if that was the case, like that you can get from S to here, right? And you would be able to go across the edge and you would have another vertex there. From there to T, that's okay. So by definition, green is just the set of vertices reachable from S. And orange is the set of everyone else. Orange doesn't necessarily reach T. Yeah. So if there was an edge left, it would contradict this picture. So we chose S in particular because we know it's going to end up empty at the end. And that all the paths will have to use it. I mean, it have to be used by all the paths. Yeah. Okay, so. Alright, so we've reached this stage where, again, the overall goal is to show that the algorithm is optimal. What we have shown, however, is that the number of paths that the algorithm takes is equal to the number of edges in this particular cut C. All right, how do I get now global optimality? What's the last step? We're really close. I think there's something more, at least direct in any case. More direct argument. So I want to argue that actually the point we've reached, this equality, actually will allow us to argue that the algorithm is optimal. But what am I missing? Or what's that last step? Yeah. Okay, so we have this inequality before, right? So I already know that if you pick any set of disjoint paths in any set of any cut, the number of paths is at most the cut, right? So actually paths is always going to lose the cut. But now we found a particular path and a particular cut that's actually it's tied, right? That means I can't push up the paths any higher and I can't push down the cuts any lower because they're always bounded by this relatively easy inequality from earlier in the lecture. Okay, so to flesh out the algebra, right? The minimum number of edges in any S to T cut is of course at most the number of edges in C, because C is a cut, right? And likewise, the number of paths that the algorithm takes is at most whatever the true maximum is, just because it's some edge packing versus the best edge packing, right? And so what did we show? We showed that the opposite ends of this inequality are equal, right? So the opposite ends are equal. So you can think of this as like some kind of like Big Mac, right? Disjoint paths that the algorithm takes is less than equal to the true maximum number of disjoint paths that the algorithm takes, less than equal to the minimum number of edges in any ST cut, less than equal to the number of edges in this particular ST cut, right? So you have this thing, except now you know that the bottom and the top are equal. It all must be equal. Okay? So, and this is actually equal, and this is actually equal, and this is actually equal. They're all equal, right? But the important part is very similar to last class, is that we have these cuts and these path packings that can certify each other to be optimal. If we didn't have any notion of cuts, I actually don't know how to argue that we have the maximum number of edges, number of paths. But it's because this duality, and it's a packing and covering problem that bound each other initially, they actually certify each other to be optimal. The cut, C, tells you the number of paths you packed is optimal. And likewise, if you're trying to get the best cut, the paths you packed tells you that the cut is optimal. Okay, so it's really important to look at both sides of this coin to be able to argue the whole thing works. This is, I think more profound or deeper than, say, shortest path or something like that, which we could analyze more directly. Okay. All right. So we have this thing where actually everything is now equal, right? And we kind of get like 4 theorems or a bunch of theorems, 3 theorems for free. Okay. So the first one, right, is nothing to do with the algorithm. Just in general, in any ST setup, right? This is like a graph structure observation. The maximum number of edge disjoint ST paths is equal to the size of the minimum ST cut, right? That's just true of any graph in S&T, independent of the algorithm. In fact, we'll develop more algorithms in coming lectures which have different properties. This is sometimes called the max flow min cut theorem, but we haven't talked about flow yet. Another name for this theorem is Menger's theorem, who studied this 100 years ago. Okay, so Menger's theorem was known even before we were studying algorithms. Okay, just as a graph structure kind of thing, graph theory. Okay, the other 2 theorems are a little bit more algorithmic. The first is that this algorithm by Ford Fulkerson that just iteratively chooses paths, and the only difference is it adds the reverse edge back to the graph. So it's a greedy algorithm, but with a residual graph. Okay, that this algorithm does get you the optimum number of edge disjoint S to T paths. Okay, so that was one thing we wanted to prove originally. And then the other thing is that the algorithm naturally finds a cut C that is also equal to the minimum ST cut. So the algorithm was also implicitly computing the minimum S to T cut. Okay. All right, so we get all those things, 1 structural theorem, 2 algorithmic theorems. So if you actually want to output the S to T cut in addition to the path or something, right? So I can add 2 more steps. So after packing as many paths as possible and updating the residual graph and stuff like that, we can just run like a depth first search from the source in the residual graph and figure out that green set of vertices that the source can reach. Okay? And then the set of edges leaving the source in the input graph will give you the minimum ST cut or a minimum ST cut. There could be more than one out there. All right. And that's right. So the size of that cut we output is equal to the size of the path packing. So both are optimal. Okay. Okie doke. So, what is now the running time of our algorithms? Our algorithm is correct, that we feel good about. Okay, so let's suppose I told you that it's not very hard to uncross paths in linear time. Like the uncrossing the paths is not very hard. If you maintain the edges in like a doubly linked list, you find a common edges and you just swap them and you swap them and you swap them. It's not that big a deal. Okay, so assuming that part is not too big a deal, let's figure out the running time. Okay, how much time am I spending per iteration? M, because I'm really just finding a path in a graph from S to T. And when I'm adding the reverse edges back into the graph, I'm not really increasing the number of edges, right? Because I removed one and I added the reverse. So I'm just finding a path in the same size graph every iteration. Okay, so I'm only spending linear time. And how many iterations do I make? Here I'm going to let lambda denote the optimum value. Yeah, lambda, okay. Okay, so actually it's just lambda, not O of lambda. But you put that all together, you get m times lambda time. Okay. What's the simple upper bound for lambda? M? Did I hear M or N? YN? Yeah, so I guess some people might think M because, oh, S should only have N neighbors or something. But I guess technically, like, you can have parallel edges and stuff like that. But in any case, M is a simple upper bound, the number of edges in the graph, because every path uses at least one edge and there's only M edges in the graph. If you didn't have any parallel edges, then N would be fine as well. Okay. All right, so anyway, but the point is that it is a polynomial time algorithm, given some graph. Okay. Lambda is whatever is the optimum value, so the maximum number of paths packed and the minimum ST cut value. Because each iteration you're adding one path. There's lots of, you'll get a million word problems that are like this in disguise, in which case sometimes you can get a good bound of lambda based on the word problem. Uh, that might be better than a pessimistic, just M or something like that. Okay. Next class will address algorithms that don't depend on lambda. All right, so good. Okay, so I just have two then. Okay, so that's the algorithm for this problem, at least for simple, directed graphs that are unweighted. M times lambda. It's a greedy algorithm, except we add the residual edges back to the graph. This very clever idea works. Okay, and the proof is very interesting. I mean, the proof itself is, of course, subtle and probably more involved than other algorithms we analyze, but structurally at a high level, it's interesting because of this whole packing covering duality and this idea that, oh, you have to analyze cuts simultaneously and they certify each other to be optimal. So many optimization problems, more than we'll cover in this class, have this sort of primal and dual, what's the other side of the coin, and using the other side of the coin to analyze it. Okay, that's sort of an important takeaway from this lecture. Okay. All right, so here's a fun problem I prepared for you guys, just to as a fun problem for you guys. All right, so what we just did was edge disjoint paths. I can only use each edge once. But a similar question would ask, what about vertex disjoint paths? So not including S and T, which of course will have to appear in every path. So only the interior vertices. Suppose that you could only use each interior, vertex in the middle of a path once. So in this simple example, there's two edge disjoint paths, right? But any path has to use the middle vertex. So there's only one vertex disjoint path. Okay. Does anyone either A, think this problem is going to be NP-hard, like it can help solve that, or have an idea to give an algorithm for this problem? Yeah. Okay, so this is a trick we've seen many times before. So first, you said, oh, if the graph is directed, for what it's worth, any undirected graph I can think of as a directed graph that always has both directions. So that's not too big a deal. But the key point is that what we're going to do is we're going to take each vertex and split it up. So the most important vertex would be this one. Okay, so this vertex I'll call A. We'll make an A in and an A out, and I'll draw an edge across like that. And we'll do that with everything else. So I guess we'll go somewhere like that. That will go somewhere like that. Vertices, vertices. So I make this, so I split the vertices, right? And then we can use our edge disjoint algorithm. Because by splitting a vertex and putting an edge in the middle, sort of like visiting that vertex forces you to use that edge, right? So to be edge disjoint is the same as to be vertex disjoint in the original graph. Okay, so classic kind of vertex splitting trick. Okay, so that's so now you guys know how to do vertex disjoint path. Great. All right, I wanted to mention another natural problem that turns out to be hard. Okay, so what we've been studying, we only had one source and one sink. It was very natural to have more than one source and one sink, right? Imagine you have like a big phone network and you need to route calls simultaneously and they're sharing wires and stuff, right? So they need to. So in something like integral multi-commodity flow, you have a bunch of source sink pairs. And each one might have a separate demand saying like, oh, the first pair needs to have 2 edge disjoint paths. The next pair needs to have 5 edge disjoint paths. The simplest case is all one. Each pair needs a separate edge disjoint path. Okay? And the goal is to choose a path for each pair so that none of them are sharing edges. So it's, simultaneously edge disjoint across all pairs. Okay? So this problem doesn't have a polynomial time algorithm. So once you have more than one source sink pair, it actually gets hard. And I described the reduction in the notes. But this is one of the famous NP-hard problems, and also a very important problem in practice because that routing phone calls or whatever is a very natural scenario. Okay. Yes. So even for fixed k, I think the reduction I have has only like k equals 2 or something. And there's one thing weird, it's like undirected graphs, k equals 2 is okay or something. There's one crazy theorem, but that's like a very deep graph theory thing. Okay. Okay, let me just briefly warm up what we're going to do next time, which I guess is like a lifetime from now because it's on the other side of the midterm. So you won't remember any of this, I think. But I have the slides prepared. So what did we not address in this class? So what if we have capacities on the edges? So like this edge is capacity 5, so I can use it 5 times. Capacity 1,000,000, so I can use it 1,000,000 times. Assemble, I can still use the same algorithm as before, right? I can think of 1,000,000 as 1,000,000 copies of an edge of 1. The only issue is that lambda can get really big. So m times lambda is not good in the presence of capacities. Another issue is, what if those capacities aren't integers, like 0.5, 0.3, and now you're allowed to do like fractional path packing. So I'll send 0.1 units of along this way, 0.2 units along that way, stuff like that. That also we need to address, right? And also destroys the whole lambda thing. I'll only point out that the stuff we did today was also a lot of structural theorems, like the maximum number of edge disjoint paths is equal to the minimum number of cut. And for those structural theorems, I don't care if lambda is big. I still have the equality, right? I still understand something about the problem. We have some issues with the algorithm. The algorithm's not efficient. But structurally, our understanding of the graph problem is completely sound. So that's good. Even with fractional values, you can kind of like multiply by a common denominator and turn them into integers and stuff like that. Okay, so that's what we'll do coming on the other side of the midterm, and we'll have lots of fun. All right, thank you.